Welcome to my channel. Today we are talking about BLoC state management in Flutter. Let's build a simple Flutter app. You start with a simple counter, use setState, and everything is fine. But then your product manager asks for a user profile, a shopping cart, and offline synchronization. Suddenly, you are passing callbacks through 10 layers of widgets, creating a nightmare known as prop drilling. A single state change in your cart widget now triggers a complete rebuild of unrelated UI nodes, tanking your performance to 15 frames per second. This is the classic state management trap. Your presentation layer is tightly coupled to your business logic, making the codebase fragile, unmaintainable, and incredibly painful to debug. To solve this, Google engineers introduced the Business Logic Component Pattern, or BLoC, at DartConf 2018. The core philosophy is beautifully simple. Your UI should be a dumb reflection of state, and your business logic should live in an isolated black box. Think of it as a unidirectional data flow powered by Dart streams. The UI never directly modifies data. Instead, it dispatches events to the BLoC. The BLoC processes these events, talks to repositories or APIs, and emits new states back to the UI. This clean separation means your UI is completely decoupled from how your data is actually processed. Let's break down the three fundamental components of this pattern: events, states, and the BLoC itself. Events are the inputs. They represent user actions, like tapping a submit button or receiving a network connection change. States are the outputs. They represent the current snapshot of your application's data that the UI needs to render. The BLoC is the brain that maps incoming events to outgoing states. For example, when a user triggers a fetch data event, the BLoC transitions the state from initial state to loading state, fetches the data, and finally emits a loaded state with the payload. Let's look at how this translates into actual Dart code using the popular Flutter_BLoC package by Felix Angelov. We start by defining an abstract event class, like counterEvent, with concrete classes like increment and decrement. Next, we define our counterState class, which holds our immutable integer value. Finally, we write our counterBLoC class, extending the base block from the package. In the constructor, we register our event handlers using the onEvent API. Every time an increment event is detected, our handler emits a new state with the incremented value, guaranteeing that state transitions are explicit and predictable. Now, how does our Flutter widget tree actually access this business logic? This is where dependency injection and reactive UI rebuilding come into play via BLoC Provider and BLoC Builder. We wrap our parent widget in a BLoC provider, which lazily creates and manages the lifecycle of the BLoC instance, automatically disposing of it when no longer needed. Lower down the tree, we use a BLoC Builder to rebuild only the specific widgets that depend on the state. It uses a selective rebuilding mechanism, meaning if the state changes but the specific data inside it doesn't affect this widget, Flutter skips the rebuild completely, keeping your app running at 60 frames per second. The ultimate payoff of the BLoC pattern is enterprise-grade testability and predictability. Because your business logic is completely isolated from the Flutter framework, you don't need complex widget tests or emulator environments to verify your app's behavior. Using the BLoC_test package, you can write pure Dart unit tests that verify state transitions with incredible precision. You simply instantiate the BLoC, trigger an event, and assert that the exact expected states are emitted in the correct chronological order. This predictability makes refactoring effortless and ensures that your app scales gracefully from a hobby project to a massive production codebase. Thank you for watching this video. Please subscribe and follow.